It just sucks what they gave up to get him.
Okay, good evening, everybody. I hope everybody in position, and let's log into the Blackboard right now. So let me see the course materials. Let me share the screen with you. So MA simple exam. Let me share the screen. Okay. So let's firstly look at where we are right now. Let's look at the information. Let's look at the syllabus. Okay, I think we have homework, right? The homework. So for example, here we have the the homework didn't show up in the syllabus, right? But on our announcement on the Blackboard, we have mentioned that. So it's gonna be due tonight, right? It's gonna be 1 week, so due tonight before 11:59 p.m. So just submit onto the Blackboard. Okay. So I just received a couple of students the request. I think the major things is that some of our students difficult to download, install, and then read into the raw data. That means the very first but important step. Okay, some of this due to unfamiliar with the software. And
Professor?
Chat, did he say the homework is due tonight?
Professor?
Yes, yes. The homework due is tonight. Yes, it's due tonight. So I will again review some RStudio information today's class, right? And when we introduce new stuff, but we will always use the similar data sets, but just different company. If you have a lucky to go home, look at our class materials, the code I provide to you, you will find that most of the data sets just use the very similar. Okay, but the most important, you need to read into that, into the
Excuse me, Professor?
Yes.
Sorry, you said the homework's due tonight?
Correct.
I'm looking on the assignment page right now. It says Thursday, March 11th, 11:59.
Yeah.
Oh,
it says
really?
Yeah.
Wait a second. I think you're right. I think you're right. I think I have did the teaching really confusing. Okay, perfect. So let me say, I want to make sure assignment is due. Let me show. Oh, March 11th. Fantastic. Yes, perfect. I'm sorry. So tomorrow, definitely, they're official, right? They're official. I forgot something. Yes. Tomorrow, midnight, right? Tomorrow midnight. Okay, perfect. So I think we have a couple of students not missing here, right? Hopefully they can understand, follow their official deadlines, right? Yesterday night. Okay, so perfect. So today I'm gonna again look into the R code, see if you have any questions, and let's go back to the syllabus. Okay, again, so let me repeat my something we have observed, right? We have some difficulty in reading the data. Sometimes due to the different computer system, the Mac, sometimes some other reason. So I think the most important thing is that we need to find the path, right, of the file you saved. Then you can call or use that file, right? And so I'm saying that for the Mac, so far I'm not quite familiar with that because most of the the computer exercise for a class and for everything required for the Windows, right? Unfortunately, ma'am. So if you use the Mac, I have two suggestions. One, use the university computer lab, right? The university computer lab, they use the Windows definitely. The other thing is that you might want to look into the Google. Actually, I think on RStudio, they should have a very perfect illustration how to install and download. I don't think there's much differences if you're quite familiar with the Mac by your own selves. And as far as the question that how to find the path, the saving path for the files, which is you need to claim at the beginning of any code, right? So I think that's probably the most one important thing. I think this is your own responsibility because you are familiar with your own computer, your own system, how to specify the path of the savings files, right? You can Google, for example, how to find the file, the path, right? The path or location in your Mac computer. I think it's a very easy solution, should be online there, right? So I think all in all, we have a solutions here if you dig by your own selves a little bit, right? Okay, so this is the first assignment, right? So we're gonna do that tomorrow, midnight. And so last class, we have roughly finished the introduction on the moving average model, right? Moving average model. Remember, our knowledge is more advanced. Last class, we give example on the moving average, which is very common. For example, when we go to the website, look at the pandemic data. The pandemic usually give you 7 days or 1 week moving average. That means they use the past 7 days average as of today's value, expected value. So this is the simplest format of moving average. So you will find that curve will be more smoothing than the real data, right? Again, this is also similar for if you analyze like a stock market, a foreign exchange rate, and other commodity investments. We use the moving average to eliminate the noise, every day's uncertainty, and to look into what the general trend, give you more accurate, expectation on the future for forecasting, right? So that's relatively easier for calculation, right? Just simply calculate the previous 7 days, the average. However, we want to summarize in the time series model, give you a more robust and a formal way how to express in the model, how to estimate the coefficients, right? So this is the moving average model. It's the idea generated from that way. So today we're going to review a little bit on the MA and the AR models, and the most important thing, look into some simple properties as well as how do we decide the order of MA or AR. That's probably one of the most important thing, right? Remember, we used like an ACF or a PACF, right? And some other information criteria to look into what the order of the lag you want to put into your time series model, right? Because you need to have an idea how long the past history will be function as input for the future forecastings, right? And intuition tells us the longer the past history is, the less influence on tomorrow's the performance. So that's the idea behind that. So today we're gonna look into the ARMA model. So this one is I like to say it's very straightforward. It's just simply based on the synthesis of the AR and MA separately. I combined them together. However, we will introduce another very important concept with so-called unit root non-stationarities. We'll discuss that. Okay, and then next week, we'll talk about the case studies. We will look into some interesting, relatively a bigger exercise for the recent linear time series model we analyzed. So for the March 24th midterm exam, my plan is that, so for such a midterm exam, I change a little bit format. Previously, I use the give exam, right, in the class lecture room. However, I found that now it's better to give you take home. That means it's more like an assignment. It's more like assignment. You have entire week to work on that. I expect that again. So there were going to be around 3 numerical questions. Okay, similar to the assignment 1. So you can think about like assignment. Actually, essentially the similar thing. I gave you an entire week to do that. So in that week, we will not meet on the week 8. So you will do the midterm exam, submit that, and and I'm gonna grade that, right? Midterm exam. And the week 9, I think this is our holidays based on our university calendar with the spring recession and Good Friday. So there's a connect together. So again, probably that week is a holiday. I will double check with that. And afterwards, we're gonna talk about a totally different new perspective in the forecasting model. So that's probably the rest of the weeks we're gonna do. Okay. So meanwhile, just let me know whatever you have a questions. So I think this way will give you more the relax on the on the knowledge preparations. Okay, but for the midterm exam, the like for example, what the questions, what the due date, I will make a separate announcement to let you know. Okay, so don't worry about the timing of that. But you want to be prepared in the week 8th, March 24th. We will do some work on that day. Okay, so now if you have no questions, let's go to the MA model and ARMA model and the unit root non-stationarity. Before I go to our details, I want to give you some big pictures. I'm pretty sure we have some, although we have learned so many things, you probably can go through something, but you probably a little bit confusing or illusion on where are we right now. Let me talk about little things here. For the AR or MA model, there is a premise. The premise is that the data has to be stationary. That's probably the most important thing I want to re-emphasize here. When we say it's stationary, you can think about, for example, that like the stock returns is volatile around small numbers, because we know that the stock market returns should be constant in the past hundreds of years. You're like a 6%, a 7%, or 1%, 2%. It couldn't be increased continuously, right? So the average around just several percentage, but there's a high volatilities. So I would like to say that's the weekly stationary, right? There's a mean is expected, and the volatilities, there's upper and the lower band. So in that situation, we can use the model to analyze that. However, sometimes we have a non-stationary models, right? For example, the GDP. If you look at the US GDP or any country GDP, it is always growth, right? Growing in the past decades. So it's like a climbing, right? So or like corporate earnings, the earning always increases. So in this case, it's non-stationary. In that case, we can't directly use ARMA model to make a forecasting. However, we need to do some work to manipulate the raw data a little bit to make it a stationary, and then we use the AR and MA model to analyze in the forecast. Okay, so I would like to say that's the so-called non-stationary, and we will look into that today. We will learn what kind of a methodology we're going to use to handle this problem. Actually, this problem is pretty common in the real world. Everything actually presents some trend and a non-stationary, right? So we will look into that. Okay, so now let's go to the course materials and introduce the ARMA models. Let's go to the MA model and let's put out the ARMA unit roots. Okay, so you will find that ARMA model is more likely an extension of what we discussed before. Okay. Okay, so let's go back to last class. We're going to talk about. Okay, so let's quickly, very quickly, to go over the materials we discussed. Last class we talked about moving average, right? The model take this format. You really want to compare the moving average model with the autoregressive model. There looks like different. So moving average model, for example, if I take the order-1 format, will be look like any time series data can be decomposed constant numbers plus what's that? 80 minus 1, what is that? That is the the shock, right? The new information shock, which is unpredicted. So that's the part, right? That sometimes in the time series, we say is innovation part, right? Or sometimes we say the white noise, right? Or randomness, whatever you can think about those properties similar, right? So we can think about any time series data can be predicted or analyzed in the way of a constant plus accumulation of previous impacts about every day's news shocks, right? So these things, however, different day and the longer the past, the weight ratio will decrease, the influence will be decreased, right? So I would like to say this is 80, this is for today. So definitely, if you look standing upon today, for example, the Wednesday, right? If I look at the Wednesday stock market returns, you definitely don't know what's going to be today's the market information or shock. It's unpredictable. However, it will be depends on the previous days, right? The previous days, the T-1, that's you're gonna do, and those things has been incorporated into the stock market prices or any other time series data, right? So this, I think the theta should be less than 1, right? Intuition tells us, right? It should be less than 1. So it's always stationary, remember here, right? So we have to be stationary, and the mean expectation is here, right? And the variance is, can we do some calculation, right? So remember, we assumed the variance of t-1 shock, there should be the same, no differences, right? So solving this equation, right? So the variance of this should be variance of those 3 items. So you can get this. If you have interest in it, let me know if you want to derive, but I basically not really required to do that, okay? But if you can derive by your own self, you probably have a better understanding on the statistical sides of the time series forecastings. Okay, so again, so the theta is less than 1, right? Theta is less than 1. And for any previous, any days, the shocks, their variance is the same, which expressed as sigma A. This is also one precondition of stationarities. If the data is a stationarity, the volatility of any day should be constant, okay? It should be constant. So autocovariance, we can calculate the neighboring 1-day lag. The correlation is like this. So the covariance between any number of lags will be 0. That's an interesting property, was different from AR models. Okay, so that means beyond than 1, right? So it's gonna be 0. So I think that will be good property because you can easily look into the autocorrelation, the correlation between any t and a t-1, the 2 neighboring days will be this, right? And this one is also easy to derive. You just simply use the covariance divided by this, right? Divided by this, you can get a correlation, the neighboring 1 day. And for any day beyond the 1 is 0s. So you will find interesting property. How can we decide is MA1, MA2, MA3 models? We simply use this, right? We simply use this. So we will check the autocorrelation functions, right, to help us derive that. So it's gonna be finite memories. That means MA models don't remember what happens 2 time period ago. Remember, this property is not for all the MA model. It's just only for the MA order 1. So MA order 1, the ACF will be cut off. Will be, I mean, only 1 time lag is significant. Beyond the 1 is insignificant. So you can simply plot ACF figures to figure out what's going to be the order, MA1 or MA2 or MA3, right? Of course, for MA2, MA3, we have a different expression of ACF. Anyway, so ACF is kind of a good criteria to judge what's the order we're going to cut off for the past history memories. Okay, so again, this is the forecast, right? So first 1 day forecast, we use that once, right? Starting from time period N 1 day ahead. So we express this because this is expectation. So we take a hat here. It's not real one. It's not actual one. Equals again constant minus theta an, right? Why? Because at time n, an is known, but an plus 1 is not, right? So this is the forecastings, right? 1 step ahead forecast arrows. Of course, an minus plus 1. That right? This is unknown, right? This is unknown. The multi-step ahead. If you take a multi-step, it will simply equals to mu, because we have mentioned that for MA1 models, any periods beyond 1 will be zeros, right? Okay, so now let's look into, so the condition, right? Theta less should be less than 1 for the stationarities, right? Now let's talk about the MA2 models, right? MA2 models. So MA2 models will take this format. So the return equals mu, some constant plus AT minus theta 1, theta 2, right? So there's the 2 lag periods. And so the most important thing here, we can express is some interesting equations nicely summarized in this format, okay? So in this case, we can remember the B represents the lag operators. So 1 period lag operator. So we take the square, are going to be 2 periods lag operators, right? And the variance will be like this. So in this case, if you want to make sure, let me see again. So the expect returns is still the mu, the constant part, right? It's easy because a equals 0, right? It's a randomness, right? And so ACF row 2 not equal to zeros, right? Because but beyond any 2 would be 0 again. So this is also intuitive, right? Because we assume the model, that means the future performance should be depends on previous 2 days, right? So of course, beyond 2 days will be zeros. Okay, so of course we can get some row 2, but it's too complex, so I think we skip here, right? But the computer will easily let you check, right? Okay, so building MA model, what's the protocols? The protocols is going to be using the ACF, the samples. The data is always sample, right? Sample ACF. So you will cut off at the lag Q, right? For the MAQ series, you just check if the spike is significant or not. Look at the ACF plot, right? Okay, so the maximum likelihood method is the method we estimate the model's coefficients, right? For example, what is the theta 1? What is the mu? We need to estimation, but you don't need to look at the mathematical details because the R software give you the results directly. Okay, and so the next we'll talk about the how to implement it in R environment, right? So for example, like the general format in the R environment, the general format will be like this, right? This is a very general format. Okay, so in the R environment, I think this is their own the publishers the path of the SIG. So definitely you need to change to your own side. Okay, and FBasics is a package we always need to use, and we need to read the table. Okay, this table used IBM data somewhere, right? The dimension is the number of rows here. Okay, so let's look at the data we have here. So let's firstly read the code, right? Read the code all through, and then we will look into how the RStudio we're going to operate. All right. So compute percentage log returns of the index. So this, let me explain what does that means here. I think when you look into this, it's better for you to look into the raw data, what it looks like. That's probably the most important thing. You will know it is a stock return or the simply stock price or closing price or average price. You need to know what they're talking about, right? So it's similarly that the raw data is kind of like the, I would like to say the price, the index price, not the return. So in the first step, you need to change, to convert to the log returns, right? Log returns. And so this one is represents that the data, the third column is what you want, right? For all the rows. That means that for the row index position here, we leave blank. That means we want all of the rows here. And the third column, we will look into in the third column what it's about. And then we will check the ACF, autocorrelation function. We are only interested in 10 days lag max, because if beyond 10 days, I'm pretty sure the stock market will not be impacted by the 11 or 12 days before, right? So again, so with the model, the order we use, we were introduced after we talk about the ARMA model, we will know that for here, that means MA1, right? 1 here, okay? And this, the first position represents how much order for the AR, autoregressive, right? If the AR and MA combine, which was gonna introduce the new stuff today. The middle position, we will talk about what is meaning of that, right? But so far, I'm pretty sure from the ACF figures, we will find that this is MA1 models, right? So we put the 1 here, ARIMA models. We save all the information output in the handler M1, ML actually, right? So the computer will give you the output, right? Give you output, right? Okay, so in the next, let me say if we have in your R Studio, I want to do this in today's class. Okay, so you can put out your R Studio software and establish on your computers. Okay. Let me see. So what we have here. Project, open file, open project. It seems that I don't have exactly the code for the MA model test. Let me try. Okay, so I think we have a lab 2 here. Let me look into lab 2. Let's look on my computer here. I just simply show the lab 2 on the blackboard. And let me show that if we have the code. In the lab 2, I think in previous class, we have a check how to do the autoregressive fittings, right? Remember, we in the autoregressive here, we use the AIC criteria, and so this is for here, and we plot the residue to see if okay. So if our model is okay, if the model is good, the residue should be looks like a white noise, random. There's no obviously trend in the residues, right? So. Okay, so afterwards, I think we don't have much related to the moving average. And let me see if we can establish a new one for today's. Okay, I think how to start with. I think the best way is simply to see if we have the data, DIBM. You want to check the class materials, we can do maybe manually here, right? If you can follow my step. So the data file is DIBM VWEW6202. Okay, so let's say if we have this data. Oh, unfortunately, I think we don't have here. Yeah, unfortunately, we don't have here. So that's probably a little bit sad. So I can't implement it here, right? I think we better have this data in our files. That's probably the best one. And anyway, so that's the ideas behind the moving average. Although I currently don't upload the data onto the Blackboard for your practice, I'm pretty sure we will have the data for the ARMA models. In that page, we should have the data on that. Okay, so to practice, let me see. Yes, for the ARMA model, we will have the data set for you to practice on that. Right. So far for this case, since we didn't provide your data, you just use your eyes to read into the code to sense what the results looks like. Right. So obviously for this data, right, to talk about the IBM, I think the IBM price, right, and we look into that IBM price, the third columns, right. So this is the things. But let me see, I think we have some IBM data before. Let me check. I think. Okay, so let me try this one. Okay, so let me use on your Blackboard, I think in purpose data, you probably have IBM 6815.txt, right? That file. So let me open this. Okay, it looks like this is IBM profile, right? If you open that txt, so it'll give you the date, to give you the price, closing price, ask price, bid price, returns. This is a value weighted returns. When we talk about the value weighted, we call them VWs, value weighted returns. That simply means that for larger value stock, they will weigh more on the returns. So we just take the weighted average. And this column, we use the equal weighted average returns. Okay, they give the data. And you can see the returns are usually very small, right? Remember those data you need to times 100 to get what kind of a percentage, right? For example, number like this is going to be negative 3.6%. It's kind of a decrease, right? And this column represents S&P 500, the market index, right? The movement. So you can see, let's just randomly look at the date on 1968, which is a pretty half a century ago. So you can see the IBM, the stock price, and compared to the general market on average, right? They are pretty moving in a similar range, right? Okay, and so you can try. I might want to save some time on today's class. If we have time, I will practice in front of you to hear. So I think that's going to be good to use that data file to practice if you can predict it with the moving average. All right. That means simply use the like this. Simply use this. That the key step here, right? So value weighted average returns. I think we have already provide for you for the IBM data, right, on the txt file I give to you in the previous classes on the Blackboard. So you directly use that column, all right, use the column. So but you need to specify which column data you want to use, right, which column. And then you just simply check the ACF, autocorrelation functions, right? I think if you just look at the first day, second day, third day, right, if they're significant or not, right, then you will decide what order of you were going to use for the moving average. Then you just simply put the order number here, right? So then you just check the solutions, right? Usually the solution will give you the coefficients, right? This is the intercept. The intercept means the mu, right? This one is simply means the coefficients associated with the AT, right? AT. So AT minus 1, right? AT minus 1s, right? This is specified this is, I think, the good, right? The lecture materials give you this. What's the model looks like? The model, I might be let you to do that in the midterm assignment, right? For example, I maybe give you the results to let you down what is the regression model looks like. So it'll be like this, right? You want to predict what's going to be return for time t, the constant, just copy that intercept, and at plus, this is the coefficients for at minus 1, right? 1465, just copy that, right? This one on this coefficients, right? Okay, so the next will be the log likelihood. Those are for the estimation process. That means that some information generated for estimating the coefficients, we so-called the most likelihood estimation. So this is not required. You don't need to understand what the likelihood means here. Okay. So here, this is used for functions, right? Used for functions. So predict is such a function that the R will directly, very easily to implement to calculate how many periods forecasting one, right? For example, in this model, you just copy the ML. The ML, remember, is all the regression information saved in the ML handlers. You just tell the computer how much periods you want to forecast. Set 5, they will give you the 5 periods forecasting. What is that, right? 1, 2, 3, 4, 5. See, they give you 5 periods projections on IBM, but value weighted returns. Okay, so that's simply for the moving average. Do you have any questions? Okay, so if you don't have, I will let me go directly to the ARMA models. Okay. So the ARMA model is just simply a combination of ARMA model, right? What's the reason we have such ideas? Remember, the autoregressive models can give you some forecasting. Moving average can give you some forecasting. The autoregressive AR is based on the variable itself. That's why it's so-called autoregressive. That means regression by themselves in the past periods. However, the moving average is kind of a regression on its own residuals, right? So I think there should be some strengths and weakness associated with each model. So people have some ideas that how about like combine them two together, right? So in that case, might be enhancing the predictability of the models. So this is a general idea, ARMA. So the ARMA model usually write in this format. So 1, 1, for example, it will simply means we take the AR order 1 and MA order 1. So that means there should be some, for example, yeah, let's use the example here, right? So we start from ARMA model 1.1 because it's easy to start, and the second thing is that they were going to easy to understand in Garch model, that this is a very famous model to estimate the volatilities. We were going to leave it for, I think, the next class. Okay, next class. So ARMA models look this way. We can write in this compact format. So you can see this side, I use the like operators, which is more compact returns. So 1 minus phi 1 BRT. So this is obviously autoregressive part. This one is a constant plus this is a moving average part, MA part, right? I think you should be familiar with that. So this part will rely upon the information on the residuals in the past periods, and or innovation or shock or information arrivals, right? And this part we depends on the levels, the data itself, right? So we can construct this. Okay, or we can break this bracket, right, and say rewrite this, right? Put RT, put the phi 1 RT minus 1, go to the other side, and write in this format. You should be exactly, you should be able to do that, right, plus AT, just simply AT minus theta, BAT is AT minus 1, right? You can write in this format. So just look closely, look at this equation, right? Look at this equation. That means the returns equals to it is self-autoregressive. This is a self-code constant. This is innovation shock for today, which is unknown, remember? And this one is AT minus 1, the previous period's shocks, we know that. So, but we give some weight because it should be less influence than today's, if we assume today's 100% impacts, right? So in that case, we estimate what's going to be the return, for examples. So that's just some, of course, stationary invariability. Basically, you don't need to understand that. This is a little bit advanced knowledge. And the mean value, that's one thing you want to be pay attention to. You should be able to derive, but I save time here, and I may not require to do that. So the mean value is the same as AR1. Okay, it's also understandable. Remember, because the MA part is basically residual part, unpredictable part, right? The unpredictable part, their mean value definitely zeros. So usually the mean of ARMA is the same as AR models. And the variance, I think there's a typo here. I think this should be in the textbook. So I neglected here for the space. You don't need to care about that, okay? Autocorrelation, okay, so it's like this. Rho1, that means the one period like will be like this format, and beyond that one, it will be phi1 relationship, okay? It's not required you to derive all of them, but it's required you to know where knowledge it is, right? Or most likely, since we do this in the computer, we might not like you to manually calculate, but in your mind, you should get some idea on what is it talk about, right? For example, Rho1 is a like period 1 correlation, today and yesterday's correlation, right? There's something like that. But beyond that one is linearly related, right, with a phi1 constant. So this is some nice summarization of the autocorrelation function. And this is usually used for judge the order of MA part, right? The PACF, the partial autocorrelation function, this is in our autoregressive models, the classroom. If you remember, we used the PACF to judge which order we were going to stop for the AR model part. So basically, you probably have these ideas here. If we have AR and MA combined together, what gonna be the criteria to select, right? That will be a little bit complex, right? And unfortunately, computer usually can give us answer directly. We're not required to manually to do that. Okay, so for the building ARMA model, if you know the model you want to use is ARMA models, okay? So again, so the specification, we don't know the orders. We don't know that what kind of methodology for order to deciding which order, because we haven't mentioned that it's a little bit complex than the AR or MA separately. But usually we use the AIC, the information criteria, okay, to see which one is the largest. And more straightforward and easier way is that in the R Studio, we have such command, auto.arima, enter the package forecast. So this function will be very easily give you just simply answer which order is the best. Okay, so if that means we probably will not require you to understand how to do those parts. What is AIC, what is EACF? No, we don't know that. We definitely don't know that. We will never. But we just need to implement in R Studio this command. They will directly give us the answers. Okay, again, so we use the likelihood methodologies. Again, it's not required to understand the details, but you need to specify, let the computer know which method you want to estimate the coefficients of the models, right? Which is MRE. And then we probably will examine the residuals, right? If the residuals is random or not. And next, it depends on your task, right? Sometimes people will concern about simply the coefficients, significant or not. Some people may be I want to use the model to do some forecasting, right? This is another task. So let me say, what's the next? Okay, so this part you can cross off. That means you don't need to understand that, just drop it. Let me talk about what part it is mean to. So the model representation is to just simply derive for the ARMA model, what exactly it is relation with MA or AR separately, how the interchangeable between them, right? For example, if I want to write the ARMA model in the MA format, what's gonna be looks like. So that means this one is obviously not for us because we only focus on the application of the master instead of like some mathematic games among them. So in this part, you don't need to look into the details. However, the next part, the unit root non-stationarity, this part is the key part we were gonna discuss, emphasize tonight, okay? So the unit root non-stationary, and this is very popular nowadays. Even you go to the company, if you do the business analyze and time series data for financial industries, for consumer industries, marketing, the unit root stationarity is definitely one of the most important questions they might be interview and ask you. Okay, so before I talk about the non-stationarity, let's talk about the random work. The random work is there's no more than the Brownian motions, right? The Brownian motion, I think we probably have heard that. It takes this format. Okay, so PT equals PT minus 1 plus AT. Very simple, very simple. So anybody can tell me, is it stationary or non-stationary?
Non-stationary.
Non-stationary is perfect because remember the coefficients should be less than 1. Okay, it couldn't be larger or equal to 1. Why I say so? Because if the coefficient, I will not look into math details. It's your responsibility to check the previous materials. So if this coefficient is larger or equal than 1, what the economic intuition that tells us? Here the coefficient is 1 or larger than 1. That means the previous impact price level or return level have a multiplying impacts on future impacts, right? Larger or equal than 1. That means the impacts will be multiplied. Think about this. So yesterday impacts will be 100%. In this case, when the coefficient equals 1, will be 100% transferred to tomorrow. So tomorrow's information will be 100% transferred to the day after tomorrow. So the impacts will be accumulated infinitely, right? It will be explosive, not mentioned when the coefficient is larger than 1, right? You can look at the duration of the AR modeling or the AR chapters. You will find that. So that all in all, if the coefficient is larger or equal to 1, that means non-stationary. That means if you look this data, raw data plotted along time series, it will be present some trend, increasing, right? So what is this equation talk about? Is that means tomorrow's price or returns or any financial criteria characteristic we're interested will be simply to the yesterday's plus today's shock, today's information, but we don't know yet, right? So this is the idea behind that. Okay, so that's why I spent a lot of time on that. You need to understand the intuition behind such a simple the format. Okay. This one is not required of my next explanation. This one is also called Markov process, which is if you learn some advanced, the statistical or data science, you will probably have heard this Markov. What is Markov? That means any day their performance will be only depends on yesterday, not beyond that. right? That's actually it's very interesting phenomenon. For example, if I want to know the tomorrow's stock market returns, it will be simply depends on today's, not yesterday, not the day after before yesterday, right? Something like that. So that means only depends on previous days, right? It's a kind of a short memories. So what is the unit root? The unit simply means it is an AR model with coefficients phi 1 equals 1. That's it. If you understand this, that's it. So this one is a unit root, right? This is AR1 process, right? And the coefficient is equals to 1. So this is called so-called unit root. And as we discussed, it is non-stationary. Okay. Duality diverges to infinity as t increases, strong memories, right? And the repeated substitution process. Okay, this one, let me explain a little bit. Although we probably less likely to let you do calculation based on this mathematics, but I want to tell you what kind of economic intuition behind these mathematical formulas. Okay, so this formula you can check that. You can check that. What is talk about? It just simply means that if I want to look at today's some economic variable, I want to make a forecasting. It will depend on the summation of all the previous everyday shocks. That's it, right? Altogether. Why we can say so? Why can say so? Look at back original equations. PT equals PT minus 1 plus AT, right? So just like the substitute. Okay, so PT equals to PT minus 1 plus AT. Okay, perfect. Then let's move forward. So PT plus 1 equals to PT plus AT plus 1, right? But remember, the PT also can express PT minus 1. So that means you can always express any day the variables at summation of the previous residuals, AT minus 1, AT minus 2, like that. So just intuition, right? Okay, now just look at like another things. Sometimes even it's random work, but there have some drift. That means the variables equals to mu plus t minus 1 plus AT. We add up a mu here, okay? Right, so it's like the mu. So this is kind of I can't figure out a really economic the counterpart to explain that. It's fairly hard. That means exactly corresponding to such a unit root. I would like to say, for example, like a GDP, So GDP, this year's GDP and the previous year GDP, right? There's some the relationship. There are differences, definitely. There's a part which is unpredictable. There's a shock. For example, last year, this year, or the 2 years before, there's a COVID, right? The COVID-19. So COVID-19 is kind of a new information we can't predict, causing the GDP fluctuate, right? So this is the part for AT, innovation. However, if you look at the past histories, look at the US GDP or any countries, it's always climbing and increasing, follow some very steady slope, right? For the US case, like 2%, 2.2%, 2.3%, there's always a growth rate, a growth, right? And as such a growth rate is sometimes is very constant. It's around 2 to 3%. So I think that number will be kind of similar to the mu here, right? It is increased, GDP is increasing, but follow some general trend. So this is a kind of a trend variables here, right? And again, so this is a unit root, right? It's unit because its coefficient is equal to 1. So that's why it's a stationary, right? And the strong memories, that means the previous impacts will be fully reflected in the futures, right? and the time trend with the slope mean. Okay, so now the question is that we have understand PT by itself. If you write in such AR1 format, the coefficients is 1 and is non-stationary. And remember, in this case, we can't use the AR model to predict because it is non-stationary. AR model only for the coefficients, which is a phi 1 less than 1, right? So this is kind of tricky here. So what is the methodology if I really want to forecast? That means I want to construct a new models. The new model variable will be the difference between any two periods. That means PT minus PT plus minus 1. I want to look at the difference. Remember, when we take the difference between any two periods, I think the non-stationarity will be canceled out, right? For example, here, the PT minus 1, that means I want to move here to the other side, will be only left with mu plus AT. And what is that? It will be moving average model we discussed, right? So in this case, if we would take the first difference, which is construct the new variables as the two differences, it will become stationary, right? That's also understandable, right? If you look at the GDP data, is always increasing in the non-stationary. But if you look at the GDP growth rate, it's a pretty steady, right? So in this case, that's the idea behind that. Yes, any questions? Okay, so if you don't have questions so far, let's look at the seasonal difference. I just list out all the possibility here, but our homework or assignment may or may not capture those because the topic in the time series modeling is fairly large and there's different situations. We can't cover all of them, but there's a possibility there's a seasonal difference. All right, that means S is the seasonal, is the periodic. For example, S equals 4 for quarterly series and S equals 12 for monthly series, right? So that means not necessarily PT minus 1, but PT minus the seasonality I'm interested into, right? For example, if I want to compare PT and PT minus 12, that means this March and the last March, the performance, like GDP values. That was probably the value we want to look into, right? Okay. And the benefits of do this way, we can cancel out the seasonalities, right? For example, we know that the summer, spring, autumn, winter, the agriculture productions, the weather is fairly different. If we look at the month-to-month differences, there's a present a strong seasonality there, right? So how to, for example, I want to compare this year with last year's and across the seasonalities. So that way differences will be cancel all the seasonality concerns that give us the real value about what's the real economy going on, right? So this is the one things. Okay, we will look into the more details in the future in the examples if we have such cases. Okay, so let's summarize a little bit. Remember, for all the model we have introduced so far, the MA model, AR model, and the first difference, that means I want to convert non-stationary to stationary. In those remarks, they're always all constant items. For the MA model, constant is a mean, the mean values. Okay, remember a little bit. Why is mean value? Because MA can express that some constant plus a combination of previous residuals, right? So in this case, definitely it's just a mean value if you take expectation. The AR models, the constant, I think we didn't derive what is the constant, meaning of the constant. It's just simply the 5 zeros. But we only can say, okay, the 5 zero is related to the mean, because I remember the mean of AR model can express like 5 0 divided by 1 minus 5 1, something like that. Like go back to check our AR1 model property. So the 5 0 not real meaning, but relate to the mean values. But if you look at the first difference model, the PT minus 1, that represents slope, right? If you draw time series data, right, it represents a slope. Okay, so here is just simple a kind of example to visualize what the real data looks like about. So if you look at the monthly log returns of a GE stock, right, 1926, 1999, 74 years. So the sample mean is 1.04. And that means that if you want to use the moving average to estimate the GE stock returns, you want to use this number to come into the mu, the constant part, right? And so if you have a $1 investment in the beginning of 1926 worth annual compounding, quarterly compounding, monthly compounding, continuous compounding, the different returns, right? In 1926 to until 1999 was going to be value. You can see this is a very high value. So the compounding effect is large, right? Remember, this average return is very high because the data we're looking into is GE monthly log returns. The monthly is 1.04%. It is huge because you can simply times 12 to get annualized returns. Remember, we have mentioned in the first day class, the log returns, the benefits of log return is that you can simply sum up together to get accumulative returns for this period. Right? So in that case, 1.04 times 12, that means on average year, you can on average earn more than 12% returns. We know this is very high for the GE stock, 1926 to 1999, right? That means $1 over that. After 74 years, if you're lucky to have such a pension, you will have thousands more than that, right? So that's kind of a very interesting mathematics here. And I believe the GE stock price is more likely a uni root, right? It's always increasing, always increasing, always increasing, right? But the return is kind of like very stationary. Okay, so let's look at the uni root test. We have to understand that if there's a coefficient equals to 1, then it's non-stationary. And the methodology, the next step, we're going to be take the first difference of the neighboring two observations to construct a new time series data and then use the model to predict, for example, like MA or AR models, right? So this is the basic idea behind that. So the next question that how do we test if it indeed existence on the unit root test? So we do this, right? For example, so let's suppose the P is the log price of an assets, right? So we can write down two models. The first one is a kind of a AR models, but take two different format. One is associated with non-constant, the other is a constant, right? Simply differences, right? So,
Professor?
Yes.
So what would we use this test for?
Perfect. So that's a good question. This test, we call the unit root test. It is trying to test if your time series following the unit root non-stationarities. What is a unit root non-stationarity? It looks like this. Let's go back to the very beginning of this here. Here. That means your coefficients of your like one period is equals to 1. In this case, the data is non-stationary. I just simply want to test if this coefficient is equal to 1 or not. That's it.
Okay.
Yeah. Why the test is necessary? Remember, all the data observation we have is a sample. It's not a full population, it's a sample, right? Only a limited. So even you have a regression, a kind of equation like this, you get some coefficients, you have no idea if this coefficient is correct or not, because your data observation is quite limited, right? So we want to do some test or hypothesis, say if this coefficient is indeed different from 1, less or larger than, right? So when simply do the test. If we after, yes.
It would be non-stationary if it's equal to 1, right?
Yes, if it is equal to 1 or larger than 1, definitely is non-stationary.
Okay.
Yeah. If it's less than 1, you can see the perverse information is converge, right? The impact is decrease, decrease, decrease. That's why it's a converge and it's stationary. Okay. And I give you example like GDP, the US GDP, right? The GE stock, the stock price always increasing, right? Those are non-stationaries, right? But if you look at their returns, they're stationary, right? So there's a differences here. Okay, so next, let's go to the test, right? The hypothesis again, so the command in the RStudio is very straightforward. Again, so it's funny, it's just simply several words, just a one line, a command, very easy. But the question is that we need to understand what's the output, the results means here, right? And what happens behind the software, right? So for example, the hypothesis looks like, if we have such two models, right? I want to establish here, a compare, right? I want to establish is if the phi1 equals 1 against phi1 less than 1. Okay, why we compare there's only two things, because if the phi1 equals 1, that means non-stationary. If it is less than 1, that means it is a stationary. So that's the only two things we are interested into, right? So this test is called the Dickey-Fuller test, which is a very famous statistician in the past decades, right? These two guys developed this test, right? It's kind of a, you probably don't need to understand the details behind its ideas, okay? But I just simply let me to go through forward, use as the simple words as possible to explain to you the idea behind that. Although I'm not require you to implement all of the knowledge, but you at least understand the output on RStudio, which we're gonna introduce later on in the examples. Okay, here I just talk about the idea behind why the Dickey-Fuller test can tell us the coefficients is equal to 1 or less than 1. Okay, so let's do this. So the Dickey-Fuller test is like this. So we assume that difference, any price difference, will be simply some time variant constant plus the autoregressive format, the betas, okay, plus t previous periods, t minus 2, t minus 3, the previous, but with some weight ratios, plus some arrows, right? And this beta, if this beta is simply we test the significance of beta against 1 is equal to 1 or less than 1. Okay, this is general ideas, the Dickey-Fuller test, right? If this coefficient, if the p-value less than very small numbers, then we can say we can reject the null hypothesis. That means there is stationary, there's non-stationarities, right? If the p-value is very large, that means we can reject. That is non-stationary. Sorry, yeah, non-stationary, right? So this is again, so we will look into the p-value, right? But if I ask you what is a Dickey-Fuller test, this test will be based on this equation. I just look into the beta, the coefficients against the 1, right? What's the relationship, right? So, but in the RStudio environment, you will see in the next page, It's very simple. You just simply type, okay, the DF test, p-value. That's it. That's it. But this knowledge will tell you what is behind this test, right? What's behind this test. Okay. Let's look at these examples. Let me see how long it is. Example. Yeah, it's a little bit. It's a little bit, right? So let's look at example. So this example is a log series of the U.S. quarterly real GDP series from 1941 to 2009, quarter 1 to quarter 4. This is from Federal Reserve of St. Louis. Okay, GDP C 96. Let me see if we have this data. Okay, I think I need to give you this data later on. Okay, so so this data, okay, and I need to upload it onto the Blackboard for those interesting data sets. Okay, so again, let's go through, use our naked eyes to go through the code a little bit, and then you later on you can implement on the computer if I give you the data, right? Just simply copy those codes, but definitely you need to change the path of the raw data saved when you analyze them, right? Again, go back to a very important question at the foremost, right? Some students may have. So if you use the deconfouler test to test that the data is stationary or not, we need to call these functions, which is f unit roots. Call this. Remember, the library means that simply means tell the computer, okay, we were gonna use this package, so you just use library. And I'm pretty sure that before these examples, the author already installed this package. So for you, definitely, I'm pretty sure you have not installed this one if you have never taken this class or some project related to this. So you probably need to install package, right? The first class we have mentioned that in the lab 1. We need to install package, which is called f unit roots, right? And the help, you don't need to do that. So there's some notation to see if the test available, right? You probably don't need to do that. So firstly, like you download the data, right? And rate dot tables, right? Download the table, the data, and the header equals t. That means you want the variable name in the raw data. That means equals to true. You want to keep the headers, right? And you want to take the first column, right? The Q GDPC 96. So okay, so yeah. And I think I need to give the raw data later on. So this is the first column. The first column probably contain or interesting variables, which is about the GDP of the US real GDP, right? Then you want to do the ADF test. So in the RStudio, the name of the package is so ADF test. Now remember, usually for such a package, F unit roots, this package is fairly big. They can do a lot of tasks. However, we only use the one of their functions. That means ADF test, right? The augmented deconfouler test. So this is the original target data set GDP. Remember, GDP is the we renamed that. Usually we will handle with the very large raw data, but we only interested in only one column, right? So in this case, it's a good habit that you want to rename a new name about some data you're interested in, right? So in this case, the GDP is your new name of the data you want to interest in, and you take it like a 4. The reason is that you want to assume, okay, this is a AR4 model for the series. That's basically assumptions. So there's no, I mean, unified rules say what kind of AR model we want to test. We usually want to give it a try and errors. So here, let's assume AR4. That means the US GDP depends on the previous 4, let me see what the units of that, quarterly, right? That means the winter GDP is probably the function of the previous 3rd quarter, 2 quarter, and the 1st quarter GDP, right? So this can be AR4 model. Okay, so when you look into that and take the enter, they will give you the results, right? The title augmented deconfouler, you will see the results output, the test here, right? Select orders for statistics deconfouler, right? P-value 0.4. So you can see that's the benefits we introduced a little bit mathematics here. Because if you have no idea what's a Dickens-Fuller test, you have no idea what's the talk about. For example, what are like orders, right? What is a Dickens-Fuller's, right? What this number means? What the number means? -1.7. What's the number means? Definitely, you probably know the p-value, right? The p-value since it's relatively large, so we can't reject the null hypothesis. That means yes, there is a unit root. The data is non-stationary. Okay, so but what is a Laguerre order? What is Dickens-Fuller? What is the -1.7? What's the meaning of that? You probably want to go back to this equation. That is the full equation for Dickens-Fuller test ideas, right? Look at here. This is the beta. So -1.74 is basically the beta values. Okay, so the order AR4, the order of 4, it just simply means that -1, -2, -3, -4, right? I want to cut off at a fourth, order 4, right? It just simply means that because this is the Dickens-Fuller what the equation looks like. So but we are only interested in PT-1 coefficients. Okay, I want to test that. Okay, so okay, so let me talk a little bit more on that. When you look at firstly at this equation, you probably have some very confusing, although it didn't raise a question, but I understand you're very confusing. That means I want to test if the coefficients with PT-1 is larger or equal to 1. That's understandable because that's the original, the random work, the unit root functions looks like, right? PT plus PT-1. The coefficient is equals to 1 is what we're concerned about. But question is that what the meaning of those kind of stuff? Why we, I mean, at other periods, variables come into play here. The reason is that I want to control the other periods impacts and only focus on PT-1 coefficients. Okay, what's the meaning of that? For example, if I don't have this item, if I don't have this, the bulk of this, only have this, it's very simple, right? That means the coefficients beta, it might be impacted by the other periods impacts. So I want to isolate, or some in statistical sense we call, I want to control the moderating impacts about other periods. So in this case, this beta probably the most accurate, right? So that's why they take this format. I just want to tell you the general ideas behind this, the format. Okay. Sometimes it's a good habit, right? For example, I want to look into a more careful analysis, right? For example, we have the GDP data, right? We have it analyzed, and I take a differences. This is a very simple function. Just simply take the difference about day 1 and day 2, day 2 and day 3, right? Look at these differences and check this AR models, the AR, right? And indeed, you will look at these coefficients, right? So again, so if you take the remember, if you have a non-stationary data, how to construct a model, you need to take the first difference and use the first difference as a new data and using the AR models. Right here, if the computer directly suggests you like 3, right? T-1, T-2, T-3. That's it, right? So we use the AR3 models. Okay, see if you have any questions for this part so far.
Sorry, you said that if it is non-stationary, for us to use the first difference, we do what?
Correct, like this. Original the GDP is non-stationary, so we take the first difference and then construct the new variables, so-called.
Okay.
Yeah.
Okay.
And then when you take difference, that data becomes stationary, right? Because the trend is basically canceled out.
Got it. Thank you.
No problem. Okay, so the command AR model. So usually the R Studio, this is a relatively easy topic. So in the R Studio, we have a command so-called ARIMA. What is the I means? The I simply means the difference, right? For example, in this data, we take the first difference, one difference, that's fine. So in the ARIMA model, that's gonna be AR orders, for example, AR3, and then we take a first difference, that'll be 1, and a comma, and MA orders. So this is a full picture of ARIMA model. So that means we firstly take the first difference of the data to make it a stationary, and then we use the stationary data to use the ARIMA model to decide which order we're going to use, right? The idea behind that. You probably wonder that is any like difference twice? It's highly possible. Now, sometimes data, even you take the first difference, it is still not stationary, right? And you probably take the second difference. What we do that, right? And then you use the ARIMA models. Right? Okay, so. Let me see if I need to use it. The exponential smoothing approach. Let me see if I need to include that. Wait.
Wait, I'm sorry. You kind of went through the ARIMA a little too quick. So you said to take the first difference of the model to make it stationary, and
Yes.
then you take a second difference to figure out which model to use?
No. I'm sorry. I think this is my bad. I think this example is good actually on the textbook. So firstly, you want to take the first difference. Right? If you know now. The idea is that you take the Dickens-Fuller test, right? For example, like this. This is a good example. You have the data, right? You have the data, GDP data. You firstly take the Dickens-Fuller test, okay? So you find that it is the cannot reject null hypothesis. That means, yes, it's not stationary, right? There's some unique root here. So you know that you take the first difference, okay? And you get the new data, and now you can analyze with ARIMA models. So for example, like your AR model. So the computer,
One follow-up. When you say trend, do you mean the residuals or shocks that you were anticipating, or do you just mean like the variability between the returns?
The trend, right?
Okay.
Okay, perfect.
So the actual trend, yeah.
Yeah. So no, this here. Let's go back to that's a good question. I think we have some confusion here. Let's go back to original. That is here, right? That is here. So look, when you take the differences, right, with the PT and the PT minus when you take difference is only some constant plus the arrows. That means there's only moving average similar left. We can easily use that. We'll take differences. That's it. Yeah. But if you don't do that, you directly forecasting PT, you'll find that coefficient is equals 1, right? So this is autoregression with the coefficients where you can't use the AR model directly because it's not stationary.
Right. Okay.
Yeah.
Okay. And so with the okay. Yes.
Okay, never mind. So later on we'll give more examples. You probably get some ideas on where are we.
Sounds good. Thank you.
No problem. So far, I think I want to leave the exponential smoothing approach for the future task. I think this one is a relatively, again, so firstly, exponential smoothing is kind of another way to make forecastings, but it's not quite relevant for the ARIMA model we talk about. So I think temporarily, I don't want to spend time on that to make you confusing or, to make your too much confusion here, but so you don't need to care about this, right? You don't care about the exponential smoothing. So just cut up this, right? Cut up this. So I guess I personally assume that we have received enough information on these parts, right? So just leave there for future talkings, exponential smoothing approach. Okay. Okay, so today I think we have probably basically go over the ARIMA models, all right, and AR models. Let me look at the information. Let me look at the syllabus, what we have here. So we have the case study. Okay, we will leave the case study of linear time series for the future usage. And what am I gonna do right now? I will upload the two data sets to the Blackboard for you, and then we can directly implement in RStudio of the examples so far here. So to try our best to eliminate any difficulties. And meanwhile, I would like to explain a little bit more on the coding tricks in the previous lab examples. Okay, I think that in the meanwhile, you may want to open your RStudios here and open your lab 1 and the lab 2 files. Okay, and meanwhile, let's upload the two data sets for today's class. Okay, let's take a few minutes break here. So Q GDP C2 Okay, so I hope you are still there, and I have upload all the data to the Blackboard. Okay, now you can check here. Let me show what I have here. On the Blackboard here in the moving average, in the moving average lecture 5, I upload the IBM VWEW6202.txt. So this is the data we're gonna to practice a little bit here. And also for the ARMA model, we're talking about the QGMPC96.txt. So this is the 2 data file we're gonna use. Meanwhile, if you look at your Blackboard, we have another thing to talk about TBO case study. This is a case study for the next class. We're gonna spend the entire day class to discuss the TBO case as some case studies. You don't need to look into so far right here. And so let's look at the IBM. Let's look at the raw data here. The raw data IBM, right? So this is the date. This is the IBM. The returns is value weighted, is equal weighted. You probably don't need to understand those things. All right. So the VW, that means value weighted market returns, because we understand in the stock market, for example, there's a 500 stocks for S&P 500, right? So the 500 stock, there is a large company, small company. So definitely the large company will weigh more importance than the small companies on the market performance. So in this case, we take the larger company, the weight ratio take larger part. So it's called a value weighted. And this one's equal weighted. That means we assume each company has the same weight, right? So in this case, to calculate what the return. So this 2 column all in all is talk about the market average, and this one is for IBM. We just simply want to compare them. So definitely this data is very clean, and we probably don't need to do either further work. And for this lecture ARMA model, we use the GMPC 96, the US GDP. So you can say year, month, day, and this is the GMP, right? So the GMP index for the US. I think the units will be billions of dollars, hundreds of billion dollars, I think, right? So this is the numbers. So you can see why it is non-stationary. It's a 1780, 1778, increase to 3,000, 4,000, 5,000, 7,000, right? 10,000 until now it's 15,000, right? 15,000. Sorry, so yes, 13,000. It's going to be $1.3 trillion for the currency corresponding to the US GMP, right? So it's always increasing. So we can say it is the non-stationary data, right? Compared to the IBM before, right? Okay, so since if it were the case, let's firstly look into use the IBM data to analyze, right? The moving average. So far, I don't need to be shy. Just simply copy the code we use in the textbook to do some practice. Now, of course, in the future, if I give you different assignment, there'll be different environment, right? But the idea will be pretty similar. Let's simply look this, right? So probably we can do this. So let's simply new file. New file. Let's initiate new file, right? You can do with me, or even faster than me, because I need to, just to explain those things. So I need to first start with the R script, right? The R script. So we can simply use the, right? We can simply use the lab 3. Lab 3. So, and name ARMA, right? .r. So we can save that, right? So lab 3. So now open that the new file. Now I can copy what I had before. So for example, right? So again,
Professor, I think your screen is frozen. I think you need to reshare if you opened a new.
Definitely, I need to. Yeah, so this is
yeah, because I still
yeah, definitely.
Yep.
So
now
what
it's
I'm
good.
gonna
Thank you.
perfect. So now what I'm going to do is that I have established a new file for this class. I have not prepared any before, so you can do similar with me right now, right? So you can establish a new file, whatever the names you want to name, right? The live stream. So again, the first way is exactly the same as we did before. So you need to set the path, right, for which file you want to saved, right? So for example, in my case, so for example, in my this is my the file for this class, right? So for this class, I have a PC, the D disk, and 2021 Spring, the 7670, right? I'm gonna open that, so you can see all of the R files and the data files saved in this. I think this is relatively easy for me, right, to handle with. So the path name will be D/2021 Spring / fin 7670. You have your own name. That's it. Okay, and so
Professor,
yeah,
can you go from the beginning how to create a new script?
oh, news.
Because
Okay, perfect. So Misha, it just simply just to click on the file, right? New file, R script, and then there's a new script come out here, right?
okay.
Yeah, and when you save that, you can save some with your own name, right? That's it.
Oh, okay.
No
Okay.
problem.
Thank you.
So now you can see from previous example, I have stored all my this class materials in the file, right? In this name. Again, so the every sign in between this quotation should be exactly legal. That means I'm not sure it's, there could be alternative way. You can try by your own self. For example, the slash, there's some direction, should be slash in this way or anywhere. This is very strict, the language, I would say the grammar for the RStudio. But sometimes there's a maybe change with different versions, so I'm not sure, but you want to pick out your own, you just exactly follow mine, okay? And then let me say, the library F basics, again, since we do the moving average for this example, so I think that we use the library, right? This library to do exercise, right? I think this is a lecture, I'm not sure, it's lecture 5 maybe. Okay, exercise 1, rate table. Remember what the data I'm gonna use. I'm very bad at memories, so let me go back to what the data we were gonna use. Let me show the data I just uploaded on your Blackboard. If you have a computer, you can access to right now. Definitely, of course, you have a computer, right? So lecture 5, moving average, this is a new data I have uploaded, which is the D IBM VWEW62202. Okay, so you download this data file on your course package on your computer, right? On the same path, right? So for me, I just simply wait a bit. So okay, so I just transfer to my RStudio here, right? You can say, I name a new data set that read into the RStudio about the data, right? The IBM VWEW6202, which is the new data I just uploaded. The data I want to amplify. I want to use the moving average to predict the returns, the interest in the column I'm interested. You can apply the method for any column, right? For IBM, for the value VW or EW, each column. Let's say if we can read them successfully, right? I select this column. and run this, right? So now, of course, we have been read into that, right? If you look at the data, right? So this is the wave 1, wave 2, wave 3, wave 4, right? So this kind of a very weird, you know, it's very weird because remember in our original raw data, we already have the name data IBM VWEW, right? You remember? So in this case, this is probably the R file name at their own, which is the name. That's the reason is that I didn't put like header equals true, right? So when you put header equals true, that means you recognize okay, your original data variable name, you want to still use that, right? It's very straightforward. So let me do this again, run this, right? And let me check. So it's like those new names disappear. So the names are in the original data is kept here, right? Data IBM VWEW, right? You want to compare with your right original. Say this is your original data, right? The TXT file, data IBM VWEW, right? It should be exactly the same as that, right? So okay, so we have put out the data, we have read into that, right? And in the next, let's copy what the textbook we use. If you want to open your textbook, right? So in the next, right? So you probably want interest in the read into the data, right? Check the data dimension, right? How many rows? Okay, of course, this is a relatively large, big data sets. That's going to be 10,000, right? And this case, right? I want to change the raw data to the log returns because previously I think this is kind of a simply daily returns. I want to convert to the log returns, right? To log returns is simply 1 plus each simple return, take the log, you become the log returns, right? You take these functions, right? So let me try this. Okay, let me try this. So let me say I create a new variable VW equals to log, right? 1 plus DA 3 times 100, right? So again, so I just simply copy the original code, right? Change the log returns. And then I simply look into the ACF VW dot right. So in this case, you can say I renamed the VW. I keep the original raw name VW, but I change the log returns. And I want to look into the autocorrelation functions to decide what's the moving average or not, right? So I simply run this. Okay, so now they give us this moving average. This is kind of autocorrelation, right? So if you look at this autocorrelations here, right? If you look at this autocorrelation here, so it looks like obviously the first one is useless. That means the correlation with its own self, zero lag, definitely is 100%. You always 100% correlate with your own self, right? However, look at the 1, 2. The 1 is obviously significant, right? The beyond is the blue line, but others is pretty insignificant. So it's very clearly. So that means we were going to use the MA1 models, use the ACF. That means the order will cut off at 1. Sorry. So if you have a more orders, right, in the future, for example, like more significant in the future, you just include into that. So using the ACF model, we basically assume that this is MA1 models, right? Okay, so so that's it. So that just exactly copy this code, right? And I will not repeat it in the next because this is very time consuming. You can do by your own self, right? Just simply use the ARMA model, use orders, right? This is MA1 models. Now remember, in this data, this is talk about the return, the stock return, and we always assume that the return definitely is stationary because the return cannot be increasing as time passed by, right? Definitely it's not increasing all the way. So it's always the stationary. And since it is stationary, we can use the moving average model to estimate that, right? So in this case, this is zeros. We don't need to take any difference because it's already stationary, right? And we don't use the autoregressive. You can use that. This is the previous class we discussed, but this class we use the moving average, right? This one. And of course, it's interesting. Your own work you can do by your own self. You want to compute like AR1 model and MA1 model, which one give you better forecasting, right? I can easily give you such assignment, right? Just use the AR1 model we learned before and MA1 model we use today and compare their residuals, compare their forecastings, right? So look at the efficiencies. So that's it. So I think just to give some illustration on what we have for the moving average, okay? And I want to close it. So in the next, since I already uploaded data and I will not repeat again, all right? I will not repeat again. So for the Deacon-Fuller test, there are similar things, but remember you need to install the package, which is F unit rules first. The F unit is root first, right? And the help here is not important here because if you can try yourself. If you type into this command, it will be show all the tests available for the unit root. There's a lot of tests, a lot of them, right? Computer, because they have for the RStudio as a product, they definitely need to contain all of the things, right, beyond our scope. But we only use the Deacon-Fuller test, the DCF. Okay, so this is the command you're going to use, the ADF task, right? So you can try read into the data to follow exactly the lines here. You will understand what they're talking about, right? And also you can also crossing validation. For example, previously we have introduced the IBM returns. The IBM returns we assume that it should be stationary, right? Because this is stock returns. So we can simply test using the Deacon-Fuller test if it is stationary or not. And I'm pretty sure it is stationary, right? I'm pretty sure it's going to be stationary. So that means you are going to reject the null hypothesis, right? It's stationary. And actually, why the stock returns is stationary is also very easy because when we calculate the stock returns, we already take the differences, right? Do you remember? For example, the day one from day two, we take the differences, we divide by the day one stock price, right? When we calculate the percentage change, so which is already different. So that's why the stock return should be naturally, definitely stationary, right? So that's the idea behind that. Okay, and so next class, I directly put the course materials, the textbook pages from page 110 to to page 116. So I'm going to talk about the core essence. That means try to establish the model we have learned. For example, like ARMA model, first differences, write the model to predict the US Treasury bill, the 3 months, 6 months bill, because there's two type of different Treasury bill is probably most important in the money market in the US financial market. You probably recently you probably heard that the bond yield will be increases and nowadays become decreases, previously increases. The increases, people probably worry about some the riskiness, right, associated with the bond, because there's some uncertainty of the economy, right, something like that. So predicting the Treasury bill, the interest rate, is a very important task for the financial and economics, right? Any policymakers in the central banks. So next, the case study, I'm going to use the linear model we have talked about, and make some predictions, forecasting on the interest rate for the short-term Treasury bill. So this basically, if you have time, you want to read over a little bit, okay? Or sometimes maybe next class, I want to introduce a little bit on the CAPM. I'm not sure if you have learned some finance classes before. In finance, we have the model to predict what the assets returns, right? And in that model, we call them a CAPM, the capital asset price model. Let me simply Google that and show you. Right, so which is this, right? The capital asset price model. So what is, I think that's probably the undergraduate financial classes we have introduced that. You want to review, very briefly review that. If you have a difficulty to understand that, you can just let me know, all right? And I will talk a few minutes to review that models. And very simple, we'll take the most simplest format of this model, and then we apply them as well as combination with the time series model we have introduced, use the tools how to predict the Treasury bill. And so that's kind of the next class case study we're going to use. Okay, I think that today's I don't have introduced the new knowledge so far, and they just spend the time to go over the ARMA model, ARIMA, and MA model we discussed today. And if any questions, we can just shoot me emails, right? And meanwhile, don't forget the homework, which is going to be due tomorrow night, right? So if you have no questions, you can leave the classroom. But if you have some questions or difficulty, you can still leave here for our further discussions. Yeah, that's it. Good night.
Good night, Professor. Thank you.
Good job. Any questions, Christopher and Aranda?
No, Professor, thank you. I'm just I'm
Yeah.
still working on the assignment. Thank you.
Sure, of course. You can leave, but never mind. If you have no questions, I want to make sure.